Hi friends, today we are going to learn measurement of electrode potential, how we can measure this electrode potential. So for measurement of this electrode potential of half cell, so this half cell is actually connected with the reference electrode with the help of salt bridge. So this salt bridge is playing a role between these two half cell, and whatever the potential we are obtaining, that is measured with the help of potentiometer. If the standard hydrogen electrode is used as a reference electrode, then the EMF, that is the EMF of the cell, will be equal to the potential of the electron. So that's why standard hydrogen electrode, we know its potential is 0 at 25 degrees centigrade. So in this way we know the EMF of that cell. And if we are using if other electrodes are used as a reference, the potential of the single electron is determined by using the Nernst equation. So this equation will help you to find out the electrode potential. So E naught of cell will be equal to E naught Rp of cathode minus E naught Rp of anode. So this cathode reduction, this oxidation, and this is nothing but the sum of the two half cell. Or instead of reduction potential, we can write E naught Rp of cathode plus E naught of OP at anode, or reduction plus oxidation. So these are the three different formulas to find the total EMF for some of the two half cell. Here you can see the diagram. There's two different vessels. This is your electrode. In the left hand side, this is right hand side. This is the salt bridge. We will study what is how this cell, electrochemical cell functions. This is a potentiometer, and electron is flowing from here to here. This is the flow of electron. It is coming this side. This is your hydrogen XII. You can see this is the standard hydrogen electrodes. Hydrogen gas is pumped inside it. So this cell will absorb hydrogen, and it will convert to gas. Okay, so what will happen? So it will be passing here. So this is the hydrogen will be accepting electrons from here, this platinum. So it will convert to hydrogen gas after accepting. So here, in case of reaction occurs, here cathode oxidation occurs, and metal will go into the solution. And when potential difference created between this is has a 0 electron volt. 0 volt is there, potential. So 0 volt is there, so not electron volts. And when potential difference created, so we can find out the EMF of this cell with the help of this potentiometer. Nernst equation. So German physicist, like a chemist, Nernst, he was from Germany. He found one equation to find this electrode potential. So we'll see this equation is actually derived from a standard change in the Gibbs free energy. So this equation is from the Gibbs free energy associated with the electrochemical transformations. So let us see what is the relationship. So relationship between the Gibbs free energy and the change in EMF of the cell. Gibbs free energy change and EMF of the cell. We know Gibbs free energy, that is nothing but the electrical work, and when the free energy will change, means it will decrease, and then the electrical work is done. How we can calculate this work? So now we know that in the wire, in potentiometer, you see in this wire electron is flowing. So we can find here electrons are flowing. So if you take the 1 mole of electrons are flowing in the wire, the total charge on that electrons will be Avogadro number into E. So it will, if you calculate, it becomes your 96,500 approximately coulomb, and this is called as 1 Faraday. So 1 Faraday is nothing but the charge of 1 mole of electron. So if you take n moles of electrons which is required for the balancing the redox reaction between your anode and cathode, so charge for n moles of electrons will be Q equal to n into F. That is, F is for 1 moles of electron. So EMF of the cell is nothing but the EMF of the cell. So what is electrical work done? Electrical work done is charge into potential difference. Charge we have calculated, and EMF of the cell is E cell, and this is equal to delta G, that is free energy. So delta G is nothing but the NF into EMF of the cell. So thus in an electrochemical cell, the system will work by transferring the electrical charge through the external circuit. So we have electrical work done with negative sign, and N is the moles of electron transferred by the EMF of the cell, and NF is a positive quantity. Now in this case, if E is positive here, if E is positive, the delta G will definitely negative. Negative means it is a spontaneous process. And if delta G is positive, delta G positive means the change can be affected only if the surrounding do electrical work on the system. So if the electrical work is done on the system, then this delta G is positive, and this is happen in case of electrolysis. So these are the condition I wrote in terms of table, so to make it clear. So delta G, delta E and condition of the process. If delta G is negative, E cell positive, then it is process. And if you take the reverse of this one, this is negative, this is positive, then this is called a non-spontaneous process. And if you take the third, and delta G is 0 and E of the cell is 0, then this condition will be equilibrium. And for standard condition, delta G naught is nothing but NF E naught of the cell. So this is the final formula for any redox reaction. So from thermodynamics, Gibbs energy change under the non-standard conditions can be related to Gibbs energy change under standard conditions. So this is the standard condition, delta G equal to delta G naught plus RT natural log Q. What is Q? Q is a reaction constant, already we have seen in chemical equilibrium. So write the value of this one NFE, and for this one NF E naught cell and RT plus natural Q. Divide by this whole by NF, so you will get this value RT ln natural Q. So E naught of the cell will be equal to 2.303 RT NF, and this natural log will convert to log of Q. And if you calculate this whole value 2.303 R by N of this, I have written this side. So N will be as it is, but whole value is 2.303 into 8.314 joule per Kelvin into 298 Kelvin. This and divided by 96.5. So this value is equal to 0.59. And this value already I wrote here, and this is natural Q. So E naught of the cell is depending upon the reaction quotient of the reaction. So as the redox reactions are there, so reactants are consumed, and concentration of the reactants definitely decreases, and then the product concentration increases, and due to the increase in product, what will happen? The cell potential will gradually decreases and the reaction at the equilibrium. Now if this production is consuming, if the product is consuming, so product concentration increases due to the increase in product formation. So as this happens, so cell potential will gradually decrease, and if it is decreasing, so reaction will be at equilibrium. Your reactant and product both are rates are equals. So this is the condition of equilibrium, and this condition we know very well, that delta G is equal to 0. And if delta G is equal to, so Q will be K equilibrium, and E of the cell becomes your 0. And in that case, partial pressure of hydrogen is also 1. So at equilibrium, this is the equation of given by Nernst. So E will be 0, E naught cell will be something value, and RT and F of natural KQ. So Q was turned into K equilibrium. So this is the equation, and finally E naught of the cell equal to 0.059 N by log of K by K. So K constant is proportional to the EM of the cell. And now if here, if K is 1, so if it is 1, then definitely the E naught is greater than 0. This means the reaction favors the product formation. If K is less than 1, so E naught of the cell will be less than 0, so reaction will favor the reactant formation. So this results fits the Lee-Chatterley's principle also. How? You know very well, the Chatterley states that if a system at equilibrium, so when any system is chemical equilibrium, so it will experience a change. If you are disturbing by pressure, concentration, so it will experience a change. When you disturb by the equilibrium by pressure, temperature or concentration, the system will try to minimize that change. How it will minimize? By shifting the equilibrium in the opposite direction. So this is the way of minimizing. This is the way of the balancing the this one chemical reactions or chemical equilibrium by using the Lee-Chatterley's principle. Now we will see the Nernst equation for anode and cathode. So for cathode, this is the metal, it will oxidize Mn plus Ne, and again if you take Mn1 minus is there, this is not minus, plus is there, and it will change to N2 plus, N2 minus N1 is the number of electron released. Similarly, if you take A and minus, it will convert to A and N of the electron. So this is the reduced oxide state, and it will convert to oxide state, and the number of electrons donated. So as per the Nernst equation, EOP for oxidation will be E naught OP minus 0.059 by M log of OS by RS. So from above relationship from here, this is the one, you can see E naught OP minus 0.059 by N, and this Mn plus, so this by this, and if M is solid, so it becomes your 1. Similarly, in the second question, this by this, you can see everything is same, E naught OP minus 0.059, and this is the difference of electron over here, and this is multiplied by log of, this is your RHS side, and this is your LHS side down. Similarly, in third question, EOP equal to E naught OP plus minus E naught 0.059 by N, and this is your A is there, and this N minus is there. So this is oxidized by reduced. So I hope you have understood how to write the Nernst equation for anode. Similarly for the cathode, you can see this getting electrons, Mn plus it is forming M. Similarly Mn2 plus is getting electrons, it is forming Mn plus, and A is, which is oxidized state, it is again converted into reduced state. So by using the same expressions, ERP, in this case we will use the ERPM like previous one. So E naught Rp minus 0.059 by N, and this is again M by this whole equilibrium, again M is 1, so this become 1 by M. For 5, so again ERP E naught Rp minus 0.059 by N, because this is your this will be N2 minus N1. So here we write N2 minus N1, I forget to write, and this will be Mn, this is this divided by this one. Similarly for this reactions, E naught Rp 0.059, this is your N electrons, and this divided by this, means always reduce divided by oxidized. And if you want to remove this minus sign, so you can take as a 1, and this will be your down, E naught Rp plus 0.059 by N. So only here sign is changed in this case. Okay, if you want to convert anode to cathode, electrode potential. So like E Rp equal to E naught Rp and plus minus 0.059 by N log of OS by Rs. So if you are writing OP, so we can write it minus EOP, or if you take a standard state E naught OP, it will be equal to minus E to the bystander Rp. For example, I have taken the zinc is losing electron and zinc is gaining electron. So EOP will be 0.76 volt, and if it gets same electrons, it will be negative. So this is just for a hint for understanding. So what are the factors that influencing the electrode potential? The factors are, already we know this Nernst equation, already we have derived. E naught cell plus minus 0.059 by N is the change of electrons, and log of OS by Rs. So this is depending upon the value E naught of the cell, temperature of the cell, and oxidation state and concentration of the reduction state. So this is our electrochemical cell. You can see very clearly M1 and M1N plus, M2 plus. This is the reduction state, oxidation state and reduction state at T Kelvin, that is 298 Kelvin. And M1 and M2 are the molar concentration. So when you are using the Nernst equation for the anode and cathode, so we write this M1 is converted to M1 and Ne. So oxidation potential of this will be your E naught OP minus 0.059 by N log of M1 plus divided by MS. And if it is 1, then this is equal. Similarly for the reduction potential, same thing as before. So ERP, E naught Rp divided by minus 0.059 by N log of M2. This is solid, and divided by your oxidized state by reduced state. You have to remember. So E naught Rp will be 0.059 by log of 1 by M2. So E naught of the cell is nothing but the EOP by Rp, and EOP is this value, ERP is this value. And if you solve it on solving, you can see here E naught Rp, this is added, this plus this is added, and finally you get this value. So E naught of the cell is, you can see here, this will be your E naught of the cell is equal to minus 0.059 by N log of oxidized state of anode, and divided by reduced state at cathode. So this whole equation is very useful while calculating or while solving the problems on electrochemistry. Now we will see the formulation of equation for different electrodes. This is the metal ion electrons. Metal is losing electrons. So EOP, E naught OP minus 0.059 by N log of this by this. So if MS is 0, and if this electron gain electrons, we can write ERP, E naught Rp minus 0.059 by N log of M by M N plus. Or if you are taking as a M1, so we can take the sign plus sign. Similarly in the gas ion electron, so let us take example of hydrogen electrodes. In this case S2 is giving 2 electrons plus 2 hydrogen ion. So EOP will be E naught OP minus 0.059 by 2 log of H plus ion whole square is the partial pressure of hydrogen. Similarly for the cathode, it will gain electrons, so we write E naught Rp minus 0.059 by 2 log of partial pressure of hydrogen divided by H plus whole square. Or if you want to remove the sign, so it will convert to plus. This will goes up, this goes down. If you are using Cl2 minus Cl minus electrode, same thing is there. So oxidation potential will be E naught of OP minus 0.059 by 2. Why 2? There is 2 electrons are there, log of P Cl2 by Cl whole square. Similarly for the reduction, ERP equal to E naught Rp minus 0.059 by 2 log of Cl, the Cl minus whole square, concentration of Cl minus whole square by partial of C2. Or ERP equal to E naught Rp in standard state plus 0.059 by 2 log of PCl2 by Cl minus. Similarly here, if you are using metal insoluble metal salt electrodes, So at anode, what happens? Silver will lose electrons, and again the silver will react with the Cl in the solutions. It will form AgCl. So we have Ag plus Cl mass, AgCl plus electrons. So this is a reduced state, this is oxide state. So E naught of AgCl will be, for this will how much? It will be EOP plus ERP. So E equal to E naught E in AgCl minus 0.0591, and E log of, we can see silver and AgCl. So AgCl is solid state and silver is in aqueous state. So this is the whole value for anodic reaction in metal insoluble metal salt electrode. Suppose you are using that metal insoluble salt in cathode. So Ag is giving silver plus electrode, and AgCl plus electron is Ag plus Cl. So for this E naught of OP will be Ag by Ag plus, and for this one E naught of RP will be Cl mass AgCl plus Ag. So this is the overall reaction. So E naught of cell will be E naught of this AgCl EM of the cell. So E naught of OP Ag by Ag plus minus, for this one 0.059 by 1 log of Ag plus, and for this will be E naught of RP Cl minus AgCl by Ag minus 0.059 by 1 and log of Cl minus by AgCl solid. So this is the whole reaction for cathodic reaction. So this is another example. Silver solid is converted to silver plus within saturated solution of silver iodide in aqueous solution, and silver plus in saturated solution AgCl in some chloride solution, and Ag is a solid. This is the equation given. So how to write in the Nernst equation? So overall equation will be E naught of cell, E naught of OP Ag by Ag plus for this one anodic, and for cathodic E naught RP Ag plus by Ag, and for this reaction minus 0.059 by 1 and plus log of Ag plus by Ag. So this is for the anodic, this is for the cathodic. So oxidized by reduced. So a next example is Ag, AgCl, KCl or KBr, AgBr and silver. So this is saturated with the KBr and this is saturated with the KCl, 0.2 molarity, 0.01 molarity. So if E naught of the cell will be EOP by Ag plus for this one, and plus RP will be ERP Ag plus by Ag in this case cathode. So for anode this is the reaction, and for cathode this is the reaction. So Ag plus Ag, the E naught of the OP of the this one, and 0.059 log of Ag plus, and in this case E naught RP Ag plus by Ag, and 0.059 log of 1 by Ag plus for this reaction. Next example we have Ag divided Ag by Ag plus and Ag2, the silver chromate in saturated solution, and this is the Ag plus in some solution by Ag. How will you write? So in this case the Nernst equation will be E naught of OP by Ag plus for this reaction minus 0.059 by 1. So log of Ag plus, this for this one anodic reaction. For cathodic again E naught of RP by Ag plus to Ag minus 0.059 by 1. So this is our 1. And the log of 1 by Ag plus. So we are solving this plus this here and this plus this here. Similarly, platinum, this hydrogen electrode in anode side, and this is the silver sulfate solution in Ag with saturated silver solution. So E naught of H2 will be this one, and E naught for RP will be this one. So if you take E naught OP H2 by H plus plus E naught RP, the whole equations, and 0.059 by 2 log of for hydrogen. So H2 by H plus, so H plus by partial plus of hydrogen, and this will be silver. So silver is there, silver by silver solution. So if you solve it, you will get this equation. This is as it is 0.059 by 2 log of H plus. If you take the partial plus of hydrogen as a 1, so it will take this by this H plus whole square by concentration of Ag plus solutions. So this is the way how to measure the electrode potential, how to write the electrode potential of a cell in equations, because all these examples are very useful for the examination. Thank you.